started justifying it. So now let me just start it proper, and then we go back to maybe motivations and a little bit of examples and justification. So this is really now a kind of crash course on cyclic cohomology. So if you haven't seen this before, that's absolutely fine, because I'm not assuming anything except a little bit of homological algebra. Just I'll tell what I'm using. Then you can just learn it now. Okay, so now to start with, A is just any stupid unital algebra over C. Even C is not necessary at all. You can work over any field of characteristics 0. Even characteristic 0 is not needed. This theory works for any non-unital, non-commutative, non-ring, whatever you want. So this is very, very general theory. A is a unital algebra over C, but let's just to be precise. Beg your pardon?
Oh, can you replace the field by a ring?
Yes, absolutely. But you have to get a little more sophisticated, but then it works, yeah. Most of machinery works, yeah. Right. So then let me introduce some notation. Cn is Cn of A is Hom, means linear maps, C linear maps from A tensor n plus 1 to C. So these are like n plus 1 linear functionals on A. So these are like n point or n plus 1 point functions Harald was talking about the other day. So it's exactly of that type, but of course very algebraic, very simple to understand. Now I'm going to define some operators, B and B prime. First of all, they're going to go from Cn to Cn plus 1. And there is this operator lambda, and then there is n, goes from Cn to Cn. And there is this operator S that goes from Cn to Cn minus 1. So a lot of players, actors in the game. So we have to swallow a little bit of algebra right at the beginning. So what these guys are, this is basically, part of it is Hookshield stuff, and then cyclic is lambda and n. Okay. So what is this? So if you have a n cochain, the elements are called n cochains. So this is the space of n cochains here, Cn. So if you have an n cochain, you can produce an n plus 1 cochain like that. Just say, use algebra multiplication, a n plus 1 minus phi of a0, a1, a2, a n plus 1, then plus minus 1 to the n phi of a0, an plus 1, plus minus 1 to the n plus 1 phi of an plus 1, a0, a1, an. I told you it's easy. So okay, so this is B. Then you check that B squared is equal to 0. Now, what is B prime? B prime, you just throw away that wraparound last term, and the remainder is B prime. And B prime squared is also equal to 0. And B prime, I tell you, as a rule of thumb, B prime is not very important. It's B that's very important. Okay. So B squared is 0, then you have a complex, which is called Hookshield complex in this case. So you go from Cn, for example, to Cn plus 1, to Cn plus 2, and so on. And you're coming from somewhere. So this is B, and this is B, this is B. So this is a cochain complex. So cochain complex means that these are vector spaces over C, and these are linear maps, and B squared, as I said, is 0. So then you can take its cohomology. Namely, you can take kernel of B divided by image of B, and that's the cohomology of this. And this is Hookshield cohomology. So this is Hookshield cohomology of A. So I denote it by HHN, for example, in dimension A, is just essentially kernel of B divided by image of B. Okay, so that's first player. Then you can define another complex, which is C and lambda. By definition, this is kernel of 1 minus lambda, but I didn't define lambda, so let me define lambda. Lambda phi on A0 an is going to be minus 1 to the n phi of an A0 an minus 1. So this is the action of the cyclic group. So this implements the action of the cyclic group. So this is called the cyclic operator or cyclicity operator or lambda operator. Right? So you look at kernel of this, all elements that are cyclic in this sense. Then you form another complex called the cyclic complex of A, which is Cn lambda. By B, you go to Cn plus 1 lambda, and then you go so on and so forth. So now, of course, at this stage, you have to worry why B of a cyclic is cyclic, right? So it's not clear. B of cyclic, you have to make sure that B of cyclic is cyclic. Why? Well, the best way to see, it's not obvious at all, the best way to see this is to prove an identity which is going to be useful anyhow. Namely, you make sure that you check that 1 minus lambda B of phi is equal to B prime of 1 minus lambda of phi. So basically, 1 minus lambda times B is equal to B prime 1 minus lambda. That's another identity you check. Once you check that, this, of course, implies that 1 minus lambda 0, B prime doesn't matter. B of phi, it's 1 minus lambda is 0. So you are guaranteed that you have a chain complex again, co-chain complex. So this is the cyclic complex. Okay, and then you take cohomology of this guy, and this is called cyclic cohomology of A. So this is, by definition, is kernel of B going from C lambda n to C lambda n plus 1 divided by image of B going from C lambda n minus 1 to C lambda n, right? Okay, so we have attached to any stupid algebra like that the sequences of spaces like this, vector spaces, that and this one. So this is the cyclic cohomology of A. Let me write it. So, of course, n goes from 0, 1, 2, 3, so on, right? And now the thing is, the most obvious thing calculation in this case is that HH0 of A, that's important to know, by the way, is HC0 of A. That's just a space of traces on A. It's very easy to see from the definition. That's just all traces on A, right? So these are all traces on A. And so these guys, especially these guys, are called, in some sense, are called higher traces, but these things are Hookshield cohomology groups. I will give you a little more intuition about that later on, right? So, but then the question is how to calculate this thing. How can we calculate these things? Now, the thing is, the only case that you can calculate by hand, if someone gives you this definition and asks you to calculate, the only case that you can calculate by hand without knowing anything is the case A equal to C. Is the simplest case. Beyond that, you have to have some good ideas. To go beyond that, no matter what, even for n by n matrices, you have to have some good ideas. So let me tell you then, what's the calculation for A equal to C? And that's an important calculation, by the way. Don't underestimate that. So HH n of C is equal to C if n is equal to 0, and is 0 if n, that's trivial to see, by the way, n bigger than 0. And HCn of C, on the other hand, is interesting because that's C if n is even. You can check that easily, and 0 if n is odd. So something interesting happens. It looks like HHN behaves better because it really reflects the fact that point is zero-dimensional. Algebra of functions on points is C is zero-dimensional, so its cohomology beyond dimension 0 is 0. So it behaves like singular cohomology, stuff like that. But this guy, cyclic, on the other hand, it exists in all dimensions up to infinity, in all even dimensions, and it's 0 in odd dimensions. So this is something that we have to understand what's going on here. So that's unlike the ordinary cohomology theories that we know, singular, de Rham, stuff like that. Okay? So that's one of the things. Now, so to go on, maybe we should look at some examples and then we go on. Yes, so let me give you another thing, which is very obvious anyhow, is that this map, that the inclusion of these complexes, right, inside here, this is the inclusion of complexes here. Any cyclic cochain is a cochain. That gives you a map, I call it I, from HCN of A into HHN of A, right? Okay, so this map, although this map is injective, of course, when you go to cohomology, this need not be injective, right? When you pass to cohomology, this need not be injective. And this is certainly not surjective, and so there's no chance this be surjective. So the thing that to understand is what is the kernel of this map, what is the co-kernel, and if you can put it into a long exact sequence or something. That's going to come next. So that's the only thing that we can say in general, the relation between cyclic and Hookshield at the moment that you can just see with with your bare eyes is that one. Okay, so let me give you an example now. So let us take M to be kind of any manifold, smooth manifold, and let's take V inside M, just any closed p-dimensional manifold, oriented p-dimensional submanifold. Okay, so you take any smooth manifold and you take a p-dimensional submanifold in that, and now I'm going to attach a so let me tell you what the algebra is. A is going to be C infinity of M, our famous algebra, right? And now define a cyclic P cocycle like this. P, F0 of P on A to be integral over V, F0, df1, wedge. I didn't put wedge, but that's okay, P, right? So that's what I had actually last time, similar to that. But now the simple exercise is to show that actually this is a cyclic cocycle. B of phi equal to 0. 1 minus lambda of phi is also equal to 0. So phi is a cyclic cocycle. Is a cyclic P cocycle. Cyclic P cocycle. Okay, so this is easy, just differential form properties. That's not a problem. For this one, it's a good idea to try your hand with that. You can do it. I tell you, you have to use the Stokes formula. That's all. Just use the Stokes formula. So this cyclic property has something to do with the Stokes formula. Stokes formula tells you that if you integrate an exact P form on V on a closed manifold, you get 0. So that's that. So you have to choose the right form such that if you integrate d omega is equal to 0, then you get this condition, a cyclicity for this one, and that's easy once we are told what to do. Okay, so now these kind of p-dimensional cycles inside. So p-dimensional cycles in M. This is inside something which is bigger. I introduced last time even. That's a space of p-dimensional de Rham currents on M, right? Cp of M. So remember this I defined to be the continuous dual of omega p of M, right? I defined it last time. So this is de Rham p currents. Duram p currents. So from here, from any cycle in M, you can attach a cyclic cocycle on A. Now, in fact, it's very easy to see that, in fact, you can go all the way up to any p-dimensional current, and you can attach a cyclic cocycle. So more generally, so let me do another example. So for any C belonging to CP, a closed P current, Duram P current on M, you can attach this guy phi C, which is going to be a cyclic P cocycle, and it's defined like this: phi C of F0, F1, Fp is equal to action of, the product of this distribution C is value on this form, F0 dF1 wedge dFp. Right? So we have this story here repeated in some sense, right? This situation here, this example here, we are repeating that example here. So you take any distribution C, which is the dual of omega p, you're acting on this form. And because the C is equal to 0, the star of C is equal to 0, the dual thing, because that's 0, so that definitely implies that you're going to get a cyclic cochain, and then being a cocycle, Hookshield cocycle is easy, just like here, just like last case. So this is now a map. It's an important map. That we constructed from closed Duram currents on currents on M. We constructed a map, say P currents on M. We constructed the map into cyclic P cocycles. P cocycles on A equal to C infinity of M. So that's the first indication that there is a deep relationship between Duram homology of currents and cyclic cohomology, right? So that's the first instance of that relationship. Any questions, by the way? Okay, I can continue then. Okay, so now to explore this relationship a little further, we need some theory. So the next topic is, I'll just tell you what is the relation between HH star of A and HC star of A. So as I said, there is that subcomplex stuff over there. So there is this inclusion, C star lambda, goes into C star. You go into the quotient. Right? So this is a complex, this is a complex, and this is a complex. So this is a total triviality, right? But what we have written, just morphism of complexes, right? So this is a short exact sequence of complexes, right? So there is, so that's the only thing from homological algebra I'm going to assume. From homological algebra, you know that if you have a short exact sequence of complexes, immediately gives you a long exact sequence in cohomology, right? So to get the long exact sequence in cohomology, it means that you go from, for example, Hn of C lambda to Hn of C to Hn of C over C lambda. And then we go into jump over next one, Hn plus 1 of C lambda, so on and so forth. But this is nothing but Hcn of A, and that is Hhn of A, and that's our old friend I. And then I have into this mysterious group C over C lambda, and then I go into Hcn of A. So you are in good shape, provided you can identify this mysterious thing. What is that group? Right? N plus 1, absolutely, yes. and then it continues. Yes? So the only thing that's missing is what is this group. So to find this group, you write another short exact sequence and write its long exact sequence, and you put the two things together, and then you find Kahn's long exact sequence. So kind of first a major result in cyclic cohomology. So let me write the other one. Just to make sure that I get it right, I don't want to spend time on the second complex. Yes, the second complex is C over C lambda. You go to C and B prime. By N, you go to C lambda and surject. So this is the B prime complex. You know, you're acting on that. So now this is acyclic. The reason for this is that this operator S that I did not introduce, but I wrote down SB prime plus B prime S is equal to 1 or plus minus 1, where S of phi on A0, S decreases dimension by 1. This is equal to phi of 1 A0 AN minus 1, right? So this shows that this guy has cohomology is 0. This is what we are looking for, it's cohomology, and this is cyclic, right? So now this gives us, for me, C over, that's 1 minus lambda. Yes, that's 1 minus lambda. And you have to prove that it is exact. It is exact. You can prove that, and then you have a short exact sequence. And from here, you get long exact sequence. That's Hn of C over C lambda. Hn of the middle term, Cb prime. And then you go into Hn of C lambda. And then you go Hn plus 1 of C over C lambda. But now these guys are all 0. And the next one is also 0. So what you get is that indeed, I made a mistake, Hn plus 1 again. Please correct me. Right. So now the conclusion is that Hn of this mysterious Hn plus 1 of this mysterious complex C over C lambda is isomorphic to HCn of A, right? So I can put here HCn of A, and then the result then is easy to see what you get. So the corollary is that, so this is Kahn's long exact sequence. So this is the IBS sequence. So you can just read this with this interpretation now. So we have, okay, HCN of A goes into HHN of A. That's I. There is a map here, let me call it B, and then you go into HCN minus 1 of A, and then you jump over HCN plus 1 of A. So now this goes from 0 up to infinity. So it's complicated, as you can see. Now this map B, that's okay. Yeah, so this is B is NS1 minus lambda, right? So we have got this B, which is NS1 minus lambda. So B is Kahn's differential. So this is Kahn's differential. So it exists on the level of cochains. So exists on the level of cochains. Okay. So now S is much more mysterious. S is this periodicity operator. So it shifts dimension by 2, and it has something to do with Bott periodicity. So it changes dimension by 2 each time, and it's more difficult to write down a formula for. So I don't think there's a formula really, a nice formula on the level of cochains for that. But there's another interpretation for S that I want to tell you about, and then once you see that in a way S is also a natural operator. So where this S comes from, so this is another definition of S. So basically you can say that putting these two things together you have got everything, but another definition for S. So once Kahn did this, he also developed a pairing HCN of A, say tensor HC M of B, for example, into HCN plus M of A tensor B. This is the so-called cup product. Right? So if you put B equal to C, your ground field, then and then use the fact that HC2 of C is isomorphic, as we saw, is isomorphic to C. So this cup product with this class, there's a fundamental class on C, which is phi of 1, 1, 1 equal to 1, for example, or maybe 2 pi I if you want to normalize things. Then from here, it gives you this map S from HCN of A to HCN plus 2 of A, and there is this map S. So that's up to some scale. That's essentially another interpretation of this periodicity operator S. Okay, so this gives us a kind of beginning, also a kind of story with cyclic cohomology. You need more results, but I think that's the first major result in cyclic cohomology that was obtained by Kahn. I think that was 1981. Okay, so let me now give several calculations of this theory so that we can see where we stand. By the way, that mysterious non-vanishing results in all dimensions now should be clear, because anytime you have a cyclic n cocycle, you apply S to it, you're going to produce cyclic cocycles in all higher dimensions up to infinity. So this can be produced like that up to all dimensions. So, so to take care of this problem, you can just do the following thing. You can periodize. So basically to kill the effect of S, basically. So to kill S, because it can become a nuisance, you just define periodic cyclic cohomology. So let us define, for example, HP even of A, which is limit of HC2I of A with respect to this map S, right? You take all these even groups and you declare two elements the same if they are the same after the S map, right? Which is the same thing, by the way, as direct sums of all even groups, right? Tensor over HC star of C with C, for example. And of course, you can define in a similar way HP odd of A. So these are the two periodic cyclic cohomology groups, even and odd. So you have to compare this in your mind with K-theory now, with topological K-theory, because topological K-theory, after Bott periodicity, we know that there are only two groups, K0 and K1, or K even, K odd, right? So that's now is kind of better relates to things. In many ways, this is a better behaved theory. For example, this is homotopy invariant, but these guys are not homotopy invariant, and so on and so forth. So now I can just say a few facts about these things. So just because I don't want to erase the board all the time, so I just use everything that's at my disposal. Okay, so what we know about this. The first thing is that, just right here, The first thing is that this guy is Morita invariant. HC is Morita invariant. Actually, both of them. So, for example, simplest case of Morita invariant, take any algebra, unital algebra, then we know that HCN of A is isomorphic to HCN of MK of A. So the algebra of K by K matrices over A has the same amount of cyclic cohomology information as this algebra A has. So that's good. Same with Hookshield. And the second one is that this guy, HC, but not HH, of course, HP, actually, periodic, is homotopy invariant. So this is very good. Is homotopy invariant. So how can you define homotopy between two algebras? Well, you just two morphisms, and then you smoothly perturb one to the other. Then you get. So then we know that these guys are kind of. Okay, so I think these are things that can take you off the ground, and there is additivity, and there are all kinds of relations like that, theorems like that. But now let me recall Kahn's calculation for C infinite of M, for non-commutative torus, and for group algebras, which is the result of Burgelia. So I'm gonna recall those results so that you have some handle on the theory, you know, where this stands. And please, if you have any questions, just maybe it's a good. Yeah. So about 0 or 1 barom, I don't know what. Yeah. But what if we define 0 for the negative groups? Oh, but if we define 0, then we are okay, right? The rest is okay, yeah. So I'm okay, I guess. Right? Okay, so yes. Yeah, that's right. For example, if Hookshield groups under some functorial morphisms are the same, then they're the same. Yeah, that's right. Yeah, that's right. So, but let me give some examples. A equal to C infinite of M, right? So M closed the smooth. And so the question is, what is HHN of A? And what is HCN of A? Right? Where A is C infinite of M, of course. So Kahn showed this. So this is an important result. I mean, the paper was published in 1985 in IHS notes, but it was already announced in 1981. So HHN of A is equal to CN, DROM N currents on M. So let me put it maybe Cn of M to refer to space this time. And this guy is equal to Zn direct sum H n minus 2I DROM M I equal to bigger than equal to 1, I would say. So these are DROM homology groups that I defined last time, right? So what is this? These are the DROM closed cycles. So these are closed DROM n cycles. So you can see, and also, by the way, HP even of A is just, honest to God, all direct sums of the Ram groups M, and so on in the even case. Okay, so so the slogan is that cyclic cohomology is the Ram homology, and cyclic homology is the Ram cohomology, because of dualities things get changed. But on the other hand, Hookshield cohomology is just the Ram currents, and Hookshield homology is differential forms. Now, so let me qualify this statement here. This is this is okay only if you use continuous cochains. So here we have to use continuous analogs of continuous cochains. So if you have this facial algebra and you look at its linear dual, then of course you don't get anything interesting. I mean, this is just too wild. You cannot do anything with it. On the other hand, if you work with continuous cochains, with distributions, in other words, then you do get something interesting in this sense, right? So let me just quickly maybe sketch the proof of this. Should I sketch the proof of this, or should I move to the next thing? Maybe just quickly tell you what the idea is, and then we move on. Okay, how can prove this? It's actually quite a tour de force. I mean, so let me just tell you. The first thing is you use this map. You define a map alpha from Cn that I defined already from Cnm to these continuous things to Cn of A, right? So send a cycle C, the Ram cycle C, into phi C, right? Well, phi C of F0 Fn is inner product of C F0 dF1 dFn, right? So now the thing that you have to check is that if you look at this complex, you have this B, and you have Cn plus 1 of A, and you have Cn plus 1 of M, and you put 0 here, and then you have again this alpha. This diagram commutes, okay? So the diagram commutes. Okay, so diagram commutes means that we do get a map from Cn of M into this Hookshield cohomology of A. And the first main result is that this induced map is an isomorphism. So the purely algebraic analog of this with differential forms and homology on the right-hand side. So let me recall this Hookshield-Costan-Rosenberg theorem. So this result has a kind of precursor in the algebraic case, Hookshield-Costan-Rosenberg theorem. It just says that the map that you have from Hn of A into omega n of M, well, A is just omega n algebraic of A. A is any smooth affine variety. I did not define Hookshield homology, but you can imagine what it is. Instead of working with cochains, you work with tensors, right? Instead of working with duals, you work with just tensors. If you do that, then Hookshield-Costan-Rosenberg purely algebraically using Koszul resolution showed that this map is an isomorphism. Now, in the case of manifolds, this idea cannot work. I mean, you have to get much more delicate, and so he has to show that first, he has to assume that first M has Euler characteristic 0. You just write the kind of resolution of a complex along the diagonal when the Euler characteristic is 0, and then you argue what happens in the non-zero. So this proof is proof of this is quite delicate in this case. So, but collectively we can call all these results Hookshield-Costan-Rosenberg Kohn theorem, something like that. Okay, so we have that. So that's the sort of slogan here is that, yes, indeed, Hookshield cohomology or Hookshield homology is essentially differential forms or duals of differential forms. That's the thing, that message that we can carry. Now, what about cyclic, though? So that's where that the long exact sequence is not quite useful, actually. I mean, if you just have that long exact sequence and these groups, yeah, because they are like two unknown in between. You have Hookshield groups and then two unknowns in between. How can you use that long exact sequence to compute that? To do that, you need some better ideas. So the better idea was to write a bicomplex. That's what Khan did. So let me write his bicomplex. This is called BB bicomplex. So this is C0. And then we have C1, C2, C0, C1. And this is the differentials here are, this is vertical differential is B. Horizontal differential is this B that I introduced. It's this one. And then you produce something on the level of cycles, C0, C1, C2, C0, C1. Now, these maps, here, these are 0. But these maps here, these are just de Rham differentials these are just de Rham differentials dualized, right? And we have this complex here also. So we have this map alpha going from right-hand side to left-hand side. So you prove a lemma. Lemma is that this alpha is commutes with all differentials. Alpha commutes with differentials, right? So alpha commutes with differentials means I already said that commutes with vertical differentials, and now it commutes with horizontal differentials as well. So it just means that this operator B of Kohn is a non-commutative analog of de Rham differential, right? So i.e. B is a, and that's what was missing basically, is a non-commutative analog of de Rham differential. So once you have that, then you are in good shape, provided you can prove a theorem, and that's a difficult theorem actually. So the proposition is that cohomology of this bicomplex is cyclic cohomology, right? H star of this, let's call this BB bicomplex, Kohn's BB bicomplex, is isomorphic to HC star of A, right? So this result, again, was proved by Kohn by a direct method, quite a difficult theorem, in fact, by the direct method. But if you introduce another bicomplex and prove that this is quasi-isomorphic with that bicomplex, then it's easier to show that that bicomplex is quasi-isomorphic to cyclic complex, and then you have a proof of that result. So no matter how you go, you have these difficult statements to prove on your way anyhow. Okay, so believing in that, then since alpha is column-wise isomorphism by this result, no, because on column-wise we saw that it induces this isomorphism between Hookshield and de Rham, between Hookshield and de Rham homology, de Rham currents. Column-wise, there are no differentials. This is 0. It's an isomorphism on total homologies. So hence, is an iso on total homologies. Right? Very nice. Now you are in very good shape, because on the right-hand side, the total homology of this guy you can just read, and it's this one. So now, total homology of right-hand side is exactly equal to right-hand side of the theorem. And that's the end of the calculation, because there are kernel of these guys give you Zn's. On other levels, you do get the Ram homologies indeed, because you have to divide. But on here, on the left-hand side, so that's very nice. Any questions about this calculation? So you see, there are several major things on the way to prove this. It's quite an elaborate statement. Very good. Yes, very good. That's thanks. Yeah, indeed. Periodic also, you can check S from HCN of A under this isomorphism to HCN plus 2 of A corresponds to, very good, to a very simple map that takes something like xn and then class of xn minus 2, so on and so forth, into 0 and then class of xn and so on. It's just a shift operator, okay? It's shift operator. So once you have this shift operator, then it gives you this state. Hence the third statement. Okay. Okay, good. So we have this. I mean, that's a kind of core computation that's in LCG applications, cyclic homology. We should know this all the time. So now I'm going to give you the result for non-commutative torus that I kind of alluded to. I'm not going to give you the full statement, just for the periodic one, and then from there we can talk about chain calculus. Any questions? Okay, so let me just erase and move to non-commutative torus. In the non-commutative case, there is another important result that's for group algebras. That was done by Burgelia, and then for groupoid algebras, done by several people. So, but I'm not going to recall those because I won't need them right now. Okay. Okay, so now the next example is non-commutative torus. So I'm going to tell you about periodic cyclic homology of A, where A is non-commutative 2 torus. Okay, so I don't think there's a need to define this. Already been used and mentioned several times. So I just fixed the generators, and relation VU is equal to e to the 2 pi I theta UV. Theta belongs to R. So Kahn did investigate this fully in that 1980, published in 85 paper I mentioned. And the result, in the case that I need in this case, is this. So here's the result of Kahn again, is that HP even of A theta, so let's call it A theta. Okay, so I have to qualify this statement. I will do it, is C2 and HP odd of A theta is C2. Now, the question is, what is A theta? Here's the difficulties arise. Right? You have to be careful. So if you define A theta as a C-star algebra, right? If you take your A theta to be C-star algebra, then this result is certainly wrong, right? Here is the thing. Cyclic cohomology doesn't work well the way I defined it. At this. Doesn't work well for C-star algebras. For C-star algebras, doing it for C-star algebras is like you want to differentiate on continuous spaces, on topological spaces. There's no differentiation on general topological spaces, right? So it's not good. It's better to look at the smooth part. So this is the smooth non-commutative torus. So I really, by A theta, I mean this, right? So by smooth, I mean what we always use when you want to do elliptic theory, when you want to do geometry with these things, you always use this. That's the sequence of all AMNs, UMVN, MNN, in Z, and these guys are rapid decay. AMN is Schwartz sequence. Is rapid decay at infinity, right? So if theta is 0, for example, this is nothing but, by Fourier theory, this is nothing but C infinity of T2, just the smooth functions. And now speaking about C infinity of T2, by the way, this is exactly like cyclic, like de Rham cohomology of, or de Rham homology of T2, right? Exactly like de Rham theory of T2. So this is like de Rham theory of So it looks like that this deformation hasn't changed at all, the periodic cyclic cohomology. But non-periodic ones drastically changes. It's very, very delicate, and we have to be careful. So you can read the original paper, but I won't mention that. Just mention. So now, what are the generators? So what are the cyclic co-cycles here? So generators. So first of all, there is this trace. Well, trace of this guy, tau of a sequence, right, is A00. So that's a trace. So this is one of the generators. There are these two, one cyclic co-cycles A0, A1 equal to tau of A0, delta 1 of A1. Oh, bad. 1 of A1. And phi of, so, and phi tilde of A0, A1 is equal to tau of, A0, delta 2, A1. So delta 1 and delta 2 are derivations. These are from A theta infinity to A theta infinity. These are derivations, right? So these derivations are fixed by this, by the values. Like any other derivations, they are fixed by the values on generators. Delta 1 of u equal to u, delta 1 of v equal to 0, and then delta 2 of u equal to 0, delta 2 of v equal to v. By these values are fixed. So it's very easy, and it's nice to check that these are always cyclic cocycles using trace property, using derivation property, and using invariant property of this delta with respect to tau. You need three properties to check that these are cyclic 1 cocycles. So that's one. That's one. Now we are short of one more, right? Because we have to produce 4 cyclic cocycles to take account of this 4-dimensional cohomology in general. What is the last one? Well, the last one is this phi of is a 2 cocycle. Phi of A0, A1, A2, perhaps the most interesting one maybe, is tau of A0, delta 1 of A1, delta 2 of A2 minus delta 2 of A1, delta 1 of A2. And then I have to close the bracket again. So this is a cyclic 2 cocycle. So this class of tau, okay, so this is psi. Let me call it psi. So these guys together, tau And basically psi generate HP even of A theta infinity, and phi tilde, generate HP odd of A theta. So now, checking that, these guys are cyclic co-cycles, as I said, is easy. In this case, you have to really work hard. I mean, just you have to do the calculation. You have to be persistent with calculation, but you do it. Sorry. But now, who guarantees that these guys are, these guys are actually independent or non-trivial? Right. Why these guys are non-trivial? Well, there are two methods to see that. Actually, maybe there's only one method, honestly. But OK, so the calculation really uses resolutions, and then during the calculation, you don't see anything. You don't see any of these co-cycles explicitly, right? So the calculation somehow magically tells you these are two-dimensional. But why these guys are non-trivial, I don't think calculation tells you, and why they are independent. So if you believe in the calculation, and if you show that they are non-trivial and they are independent even more, then you have found the basis. So that's what I want to do in the next 5 minutes that I have. If that's okay. Maybe 4 minutes. Okay, so how can we show that these guys are non-trivial? Well, I don't think there is anything about trace, right? Well, this is different from 0. This is obvious because there's no relation. It's a trace. It's just a space of cyclic homology. It's just trace. Okay, so for HC0, at least this is okay. Why phi, for example, the class of phi is different from 0? Well, let us compute that on one particular element. Phi of u is what? This invertible u. But phi of u is trace of, right, u delta 1 of u. Now, what is this guy? I'm sorry? Oh, yes, u and u inverse. Thank you. Yes, absolutely. Phi of u and u inverse. Let's compute that. Then we get trace of u delta 1 of u inverse. Now, you use the fact that delta 1 is a derivation. Then you apply this to this identity. You show that u delta 1 u inverse is, in fact, nothing but 1 or minus 1. And trace of 1 or minus 1 is 1, right? So trace of plus minus 1 is plus minus 1 is different from 0. OK, now, but why this calculation shows that phi is not trivial? But why? So this is a question, why this shows C1, for example. It's not B of something. Well, what I have done here, really, if you notice, this U is the generator of K1, right? One of the generators of K1. Is an invertible element because we know that K theory is K1 is generated by invertibles, right? So it's a generator of K1. And somehow I have paired HC1 of A with K1 of A, and I have produced a number, right? And in fact, this is the formula for pairing. This formula that I wrote here is formula pairing, right? So this element is a generator of K1. So this element definitely is not 0. If the result is not 0, it means that the class of this guy here cannot be 0. Right? So then your work is back to defining such pairings. These pairings can be defined in general. They were defined by Kahn. So these are examples of Kahn's Chern characters. So in general, they are defined like this. So if you just give me a minute, they are defined by this. H, in general, they go like this. HC 2n of A, sorry, 2n of A, tensor K0 of A into C, and then you have another one, HC 2n plus 1 of A, tensor K1 of A into C. You show that these pairings are well defined. So my plan is to, using these things, to write down Kahn's index theorem. There is an abstract index theorem. And to repeat this calculation now with phi, with the psi also. It's a 2 cocycle. To show that psi is non-trivial, you apply this psi to Riefel's idempotent E. You get the value 1. It shows that this is non-trivial. And then to show that they are independent, you have to do a little bit of work. Essentially, then you show that, okay, you have produced the basis for HP even and HP odd. But the message really is to get this kind of non-commutative Chern-Bay maps, non-commutative, these are Kahn's Chern character maps. And once I get this index theorem, then I can move to next subject. Then I can talk about these metric aspects, Dirac operators, because this is about Fredholm modules, so go about Dirac operators. So I think I better stop. Thanks.